So good afternoon, my name is Michel Belda. I'm presenting this work that we're doing at Charles University with my colleagues. Actually the presentation and most of the work has been done by my colleague Peter Husáru. Unfortunately couldn't come to this conference, but I hope I can give it justice. We're talking about urban environment in regional climate models. As we saw in the previous second presentation, the importance of urban surfaces and their treatment in regional models is pretty obvious. I don't have to go through that again, I guess. But we're trying not only for the climate interactions, but also for interactions with atmospheric chemistry. There's a number of interactions in the climate system that are connected to urban environments, and in this talk I will focus on these three. Well, actually in our analysis we focus on these three. The first one is the direct effect on meteorology through that urban heat island effect that we already saw. Second one is the influence on air quality or atmospheric chemistry due to urban emissions. And the third one, a small one but probably important one, is the effect of the changed atmospheric chemistry on the climate back through radiative interactions. So first I'll start with the urban heat island itself. We saw the presentation, so I don't have to repeat that, but there's a number of processes that contribute to that urban heat island. Most of them have to do with accumulation of energy, trapping the solar radiation, then putting that back in, and also some effects on soil moisture, well, not soil moisture, but moisture in the cities, and also some impact on turbulence. Of course, the regional models are pretty coarse in resolution to resolve those urban impacts. If we're talking about what we call high resolution in regional climate modeling, 10 by 10 kilometers is very coarse. If we take the example of Prague, which is the biggest city in our republic, it can be represented by only 4 grid points in this resolution, 10 by 10. So that's not sufficient. So we need to go to some kind of treatment of urban surfaces. What we use is the single layer urban canopy model, adapted from what is in WRF model, but we adapted it for RCM4 regional climate model from ICTP. It's again single layer, so very simple one, but for the longer runs that we need for climate modeling, it's probably the only option to have a very simplified model. The other option that is directly in the RCM model, because there is the CLM scheme, which also considers some urban effects in fractional land use. So that's the other option, and we basically did 2 sets of experiments. One with RCM and that single layer urban canopy model, coupled with that original land surface model of RCM BATS, and the other set with that CLM submodel of RCM. And all these experiments are basically sensitivity experiments, what if scenarios. Basically it's a scenario, what if there were no cities. So urban experiment is the reality where the cities are, and no urban, what if there were no cities. I won't show all the variables that we could look at. I'll just picked the most important ones. So basically the most important one is the near surface temperature. If we look at how it looks in summer, the upper plot shows daily change or sensitivity to that removal of cities, so urban minus no urban. On the left side it's with BATS and LUCM, and on the right side is with CLM. Lower plot shows the same thing for night. As we can see, the importance is more in the night, as we saw in that previous presentation. Both models agree on the main features. So yeah, the cities are warmer than the surrounding environment. But if we look in the daytimes, we can see some difference. Here in Buds, the influence is much more spread around the area. It's not confined to the cities themselves, like in CLM, where we can really see the spots where the cities are. In Buds, the influence is very much spread around. Same pictures for night, and this is kind of puzzling. We see, well, I don't know if you can see that the shades are very small because the values are very small. So Buds shows some increase in temperature, while CLM shows decrease in temperatures, with the cities included, which is kind of puzzling. We don't have an answer for that yet because the results are pretty new. That's some interesting result. The other variable that we look at, mainly because we are interested in that link between chemistry and air quality, is the boundary layer height, which is one important parameter that goes into chemistry models. So we see that both the models agree on the increase of boundary layer height with the cities included. Again, the CLM, in CLM the effect is more confined to the cities themselves. In Buds it's rather spread around the cities as well. I can skip this one. So that was the first part. The second part is the influence of emissions. The emissions that originate in the city. The influence on atmospheric chemistry. So again, we did sort of a sensitivity experiment, what we call, or what is called an annihilation experiment, where we take one set of experiments where you take all the emissions that are in the inventories. We use, by the way, TNO inventory, and another set of experiments where we remove the emissions that originate in the cities, in the urban areas, where cities are considered places with over 500,000 inhabitants. Smaller thresholds is in Eastern Europe. So let's see what are the results. With NO2, the result is kind of expected. In the cities, there's a large increase of NO2 concentrations, but in the surrounding areas, the concentrations are increased as well. With ozone, we see, of course, a different picture. The places in the cities where we have a large input of NOx, they can see by the way of titration of ozone, a decrease of ozone concentrations in the cities themselves. But also, you can see increase in the surrounding areas. With SO2, basically the same picture, increase in the cities, slight increase in the surrounding areas. I can skip that. Same picture for PM, increases all over the domain, with the main increase in the cities. So that's the second part, and the third part is the effect of that changed chemistry back on climate due to some radiative interactions. So basically the experiment is again the same, either we include the emissions or we don't, and check out the result, but this time the result on the impact on climate. And what we can see here on incident shortwave radiation, the impact is very small, the numbers are very small, and it's not statistically significant in most of the areas. With temperatures, which is what we're interested in mostly, again, not very statistically significant impact, and what's more, the numbers are this time even smaller. It's, if you can see that, it's 0.04 degrees, so not a large impact. So let me sum up, I guess, with the main message that I would like to say is that the largest impact of urban surfaces is due to that well-known urban heat island effect, rather than by the emissions. The emissions have an impact, but mostly on the chemistry, not on the climate, or at least that's what we see in our simulations. So that's it. Here are some references to publications that have already been published or that are in preparation right now, and with that I thank you for your attention.
Thank you, Michel. We have time for a couple of questions. Yes, sir.
I think maybe you switch actually the temperature and precipitation response.
I didn't show precipitation response.
Okay. Okay. So the first one, the first impact that you showed, what was it exactly?
In which part?
Like
the last part?
Yeah, the last slide, not the last, the one before.
This is surface temperature, and this is radiation, shortwave radiation.
Shortwave radiation.
Okay. They're pretty much connected together, but.
And you don't see any temperature decrease over the city, actually, just by.
No. This is the impact of emissions, not the impact of the city surfaces.
Okay.
So impact of chemistry back to the climate, feedback to the climate.
Yes. So if you have a reduction of shortwave, you should have maybe a signal in the temperature, right?
There is some signal, but it's very small. The numbers are like 0.04 at max. So.
Any more questions? No? Everyone is eager for coffee? Okay, so let's give a round of applause to all speakers. So after coffee break,